Thank you very much for the introduction. So thank you everyone to be here to listen to my talk. Today I'm going to talk about SIMD programming and processing of graph algorithms on GPUs. As he just mentioned that it's really just a marriage between graph and GPU. So it's about two things. Let's see how these two guys behave together. I bet everyone agrees that graphs are everywhere, starting from the morning, like our generation, right? We typically use Facebook to check new feeds, and actually it's based upon social network. If you want to navigate from airport to here, you are using, single source shortest path or similar algorithms. If you think SIMD is an interesting paper, please go ahead and Google it. Well, actually, when you Google it, it's actually working on a web graph to figure out the web page of your interest. There's a lot of applications out there. They are based upon graphs. I definitely cannot enumerate them one by one, but I think it's very safe to say graph is everywhere. Where on the other hand, graph algorithms are working on those graphs and extract very valuable insights for our daily life. For example, I'm still using the same graphs over there in the right side, and I'm listing the algorithms like computing on those graphs and extracting valuable insights for social network, friend recommendation, for navigation using shortest path, or PageRank. Not need to mention, Larry Page invented this and they used this as a prototype to build this giant of Google, right? Matrix factorization similarly for Amazon. Well, graph is everywhere. Graph computing is very insightful, but unfortunately, graph computing is also not easy. Well, give you a very intuitive example, right? When we're learning about algorithms, graph algorithm is always the last chapter of your algorithm book, right? So you know that. It's intimidating for us. Well, here I'm not saying it's intimidating for us, it's intimidating for the machines. Right? In the middle, it shows the theoretical complexity of graph algorithms, saying, you can see here, the complexity is either E or several times of E. If you take a look at the graphs here, we see trillions of edges, or tens of trillions, hundreds of trillions of edges. So it's a lot of data. And when you run the power graph, which is a very popular graph framework, on a relatively small Twitter data set, which is 53 million vertices, 2 billion edges, it takes tens of minutes to hours to figure out those kind of computations. Well, if you just give an imagination, if you're navigating on the highway, you make a wrong turn, which is typical. Everybody makes mistakes, right? Do you want to wait tens of minutes to figure out the next turn? Well, I bet you do not want that. Actually, it's not like that, right? But because here we're talking about this, I'm giving you an illustration about that. We need graph computing to be faster, right? Well, we need it to be faster, and it's very fortunate right now. There's a very good processor over there. They can provide very, very impressive computing power and data delivery rate. For example, we see here highlighted, it gives you 120 teraflops computing power and nearly 1 terabyte per second throughput. This is, tremendous, right? Why is like that? I'll give you a very high-level impression about why it's like that with two things. First is processor, second is memory. They both are hierarchical. So you have a couple of multiprocessors, and instead of each multiprocessor, you have a couple of cores. Taken together, like V100 GPU have 5,000 of cores over there and supporting millions of threads to do the computation. Well, on the other hand, you have the hierarchical register, shared memory or L1 cache, L2 cache, and global memory. They deliver you different access latencies, like 0 cycle, because it's already in register, so you can compute immediately, or it's in shared memory or L2 cache, global memory, etc., different latencies. So it tells you that you want it to be still sustain the locality, right? Well, GPU has a lot of things. We're not from NVIDIA, so we're not selling it, but I'm telling you some caveat or takeaway here. That is, GPU is SIMD in nature. That means you have millions of threads. Like thinking about it, you have a general has millions of soldiers. He cannot talk to every soldier, right? He have to talk to a group of soldiers at a time, where they need some hierarchical management. Similarly here, they manage the threads in a WOP or a SIMD group. And then every time you have 32 threads, they're going to schedule in the same instruction to the computation. Well, that being said, if it's not obeyed, then your performance degradation is going to be suffered. Well, this is something everybody knows. And I want to give you another caveat is when you're accessing some data, it's also similar. if you ask those consecutive threads to access non-adjacent data, then you're going to also suffer from the memory access degradation. So with the SIMD in your mind, let's move on. So we say GPU is very good to map those dense matrix computation because it's very regular. It's like image processing, right? So that's also the origin of GPU or graphics processing unit. Well, if you map graph on GPU in the middle, you see that it's a twisted mapping because graph is what? Complex in nature. So as I said in the netting talk, I'm saying GPU's SIMD graph is complex, so that's why they marry, right? So you combine some blood from this one, some blood from that one, so it becomes SIMDX. Okay, so that's why we bridge the gap between graph computing and GPU, well, in terms of name at least. Okay, so it's a little bit motivation. Now let's move on to what is exactly graph computing and then how we do it. So for example, using single source shortest path as an example, if we are computing on this toy graph which has A to I 9 vertices and a couple of edges, the value, numerical values on top of those lines are the edge weight. Assuming we start the traversal from 0, and then we go to B and D, correspondingly, we update the distance array with the distance of A as 0 and B and D with 5 and 1 respectively. So when we proceed to next iteration, we see different colors of the vertices. So this darker brown means it is active right now. You have to compute on this vertex right now. And those slightly lighter ones means they just get updated in this iteration. And that also means it's going to be active in next iteration. So similarly, we work on B and D. We get E and C being updated. You continue like this, you get another one. Well, some of you may question, okay, you are not using Dijkstra, right? So here we didn't use that is because Dijkstra is has very limited parallelism because it only allows the shortest one to proceed at a time. So here we allow those guys who get updated, all of them, you can go ahead. Because think about GPU has massively parallelism, right? And you can continue like this until you have no update to perform. It's also the time you can terminate your computation. Well, this is an impression to you. Let me summarize what's wrong with it. First, you only allow or you only experience a portion of vertices to be active. That actually means you cannot compute on, or you do not have to compute all the vertices at a single iteration. You only have to compute on those darker brown ones, right? Second is various active vertices are totally different. If you use social network as an example, or Twitter, like our president has millions of followers. I have 6 followers, right? Well, yeah, that's true. So it means if we assign the same amount of threads or same number of threads to these 2 vertices, you suffer from workload imbalance, right? Synchronization is also necessary. As we can see here, from one iteration proceeding to next iteration, you have to get updated value from the previous iterations in order to proceed to next iteration. Otherwise, you're going to get skewed updates, or you're going to your synchronization or convergence is going to be postponed. So that's all those challenges you want to deal with. And then SIMDX is here to bridge the gap. Then it's here to solve these problems, right? To solve only a portion of what is being active, to solve this workload imbalance, to solve this synchronization. Well, because we have limited time, I can only focus on the first one. Assuming we have vertices E and C being active, let's see how we work on it. We work on a neighbor of E and C, which is, assuming we have multiple threads, then definitely we parallelly processing E and C. So we get work on B and F, which is a neighbor of C, and BDF, GHI is a neighbor of E. And then we put neighbors together, and then we work on the distance array, and then we generate an active list. This is how related work on it. So we say first, it has to use 2 multiply E number of space to cache this active neighbor list. And also, it has to go through scanning of the distance array a couple of times in order to extract the next active list, right? And also the active vertices BFHI in the bottom is out of order. It's not good for memory access pattern as we are in the system conference here, you know that. So to summarize, we have a couple of vertices. Oh, sorry. Okay. I mean, it's easier for you to remember because that's why I summarize it. So we have a couple of vertices, and then we load neighbors into a construct active neighbor list in the left side, and then we do filter neighbors, and we get the active vertices. Those pink ones means, or the brown ones means you have a problem over there. So then we propose bullet filter, or some people also been using it for their own work. How we work on that? First, we work on the E and C, and then we simultaneously update the current distance array. And afterwards, we compare the previous distance array and the current distance array. Use bullet primitive provided from GPU to generate an active list that's in order. Well, the technical is pretty complicated. I mean, I just give you an impression. If you have any further questions, definitely let's talk later afterwards. So I'm giving you some summarization first. We only use V space because we do not have to construct the active neighbor list. And second, we use one filter step in order to generate an in-order active vertex. So what is this list? To summarize is we do not have to construct the active neighbor list as before. So we basically know the neighbor and directly go ahead update the metadata. And then you scan the metadata in order to generate active vertices. And also the active vertices is in order. Okay, so that's that. And we also figure out scanning the status array actually takes a lot of time, right? Think about it, you have very few active vertices. Then we say, okay, why don't we just use autonomous operation? I know autonomous operation is a lot of overhead. Everybody wants to avoid it. But if you have very few autonomous operation, it sounds to us it's good, right? So we also give it a try and figure out it's pretty good for those very few iterations in the initial and last iterations of graph traversal. So how it works, assuming we're working on B and D, which is very initial, the second iteration, and then we work on the neighbor list, and we go ahead using autonomous operation to update the distance array, and then we generate a negative active vertices list, which is out of order. So this is summarize how it works. So taken together, batch filter is not good because it consumes a lot of memory, and GPU has very few memories over there. So we use bullet filter to make it better, as well as consuming less memory. And then we say, okay, some iterations may even suffer from scanning to generate active vertices. So we go ahead and use autonomous operation to do that. So that's the first task management, or only a portion of the vertices are active, how we deal with it. And the second thing is we think, well, programming on GPU is not straightforward. So we go ahead, figure out the most important things in GPU-based graph computing, and then we say, okay, you only have to define those APIs. Basically, it's the framework selling, slide. See how it works. Assuming you have those top are the vertices or the task, you have different tubes. Those ones has higher shadow means they have more workload. Those ones have an inactive vertex inside of it, or found inside of it means it's not active. To mimic, you have only a portion of vertices being active. So first, you go ahead, filter out those active ones, definitely, and then you classify them into different groups. Like 0-3 is a group with very small workload, while 1 and 5 have a lot of them. And then you do synchronization, and then you map them onto different number of cores. Like you have a lot of workload, then you go ahead and use a lot of cores, right? You have a very few, then you use very few cores. So that gives you an impression, no matter you are from a giant frontier or a small active vertex, it's easily similar because we're trying to make sure everybody take care of similar amount of workload. So then we say, okay, the summarization is you only have to tell me which vertex is active and how you want to compute on the edge, and then how you want to combine those edges together in order to generate updates to the vertex, right? So this is the ACC programming model, how we derive those kind of essential component for you guys to simplify your programming on graph computing on GPU. Okay, so taken together, we evaluate SIMDX on a couple of those data sets, starting from Facebook to Twitter, those vertex count and edge count are over there. So definitely, showing result means we're pretty good, right? So we have x-axis are different graph data set from FB to Twitter, and time are like millisecond. We run the PageRank for like 5 iterations, I believe. So we see pretty good speed up over Gunrock and Galois, which are like very popular. And also we run against Ligra and others. We didn't have including all of them, but these two will show you that it's pretty good performance. When you zoom in, you can see the performance is still very good. We also compare it against the BFS. So we see that still x-axis is different data set, y-axis is the time for traversal and get a valid BFS. We see that the speed up over Gunrock and Galois is still observable. Well, you may also notice in some portion that like RD, which is a random graph, you see that the performance is slightly worse comparing to Galois. I mean, not slightly, it's definitely worse, right? Let's not be shy about it. So the reason is very straightforward, because RD is a graph that comes with uniform degree distribution. So that means your workload, task management, to put this in this bucket, this in that bucket, and to schedule those kind of things, those are useless because they're the same, right? So it's overhead. There are more sort of technical contributions like synchronization and programming abstraction, how we do that in GitHub. All of them, you can be found that in GitHub or can reach out to me to figure out all those details. Thank you.
Questions or comments? Go ahead.
Hi, I'm Jiwon from Hanyang University. Good talk. There are many different kind of graph algorithms and many different variants. For example, data stepping algorithm for parallel shortest path computation and things like that. So out of all those graph algorithms, have you found any graph algorithm that your technique do not work well? Or can you think of any graph algorithms that your algorithm do not work well?
Okay, that's a very good question. Yeah, we should not hide it, right? So basically, if you take a look back, the programming asks you to define the active vertex, asks you to do computing and combine. So those things only work on something that can fit in this sort of paradigm. If you go to some sort of graph-based machine learning, like collaborative filtering or multi-layer perceptron, those kind of things that does not need those kind of techniques may not work. Or the control flow is way beyond just active compute combine. Maybe it's active compute, or something like that. Compute combine. If you go beyond those kind of sequences, it will not work. Thank you for your question.
Hi, I'm a PhD student. Good talk. I was curious about your programming interface. What do you think? What's the difference between your interface with the previous graph processing framework? Because they also propose some programming interface.
Okay, it's also a good question. So yeah, because I think you are coming from the background that there's so many programming interface, right?
Yeah.
Vertex-centric, edge-centric, gas, GS, or whatever, right? You can see all of those kind of things. So here, I think I can differentiate it from maybe 2 ways. So first, this is the programming model for graph computing on GPU. So when you put it on GPU, it automatically means that you have to deal with those hierarchies of memory, hierarchies of threads, like a WOP, a CDA, or block. Then here, we are trying to really hide those those programming complexity originated from the hierarchy of thread management and memory management. So that's something that vertex-centric or edge-centric or gas, those things which are designed for either external memory or CPU-based things, which they cannot cover. And the second thing is also based upon GPU, is that we're also taking care of the performance. So say we do computing on edge and combine on vertex. It means we actually try to use some buffers to combine those updates without autonomy operation. So I think those are the two uniqueness I would identify.
Yeah, okay, thanks.
Thank you.
A brief question.
Yes, go ahead.
Thank you for a really, really good talk.
Thank you.
In your examples, you've always, probably because it's a simple example, you've always used the edge attributes was just a single number, and the distances is just a single number. If I have some machine learning workloads where I have a vector at each edge or a vector at each node, can I still use this?
Okay, I'm working on that right now. So it's a very good question, right? So I think which neural graph going to talk a little bit about it, right? So yes, because when it goes to high dimension of vertex attribute, then those single entry distance array will not work, right? So this one cannot work. Let me be straightforward.
Well, I think the
So-
API could still work, right?
Yeah, I mean, you're going to have to deal with the high dimension complexity because some of them may be a lot of zero portions, some of them would be very few portions. So we're also working on that. I have some work in progress. I think we can take it offline.
Yeah, thank you. Very good talk.
Thank you.
Let's thank the speaker again. Great talk.